Good day, one and all. This video is being made to explain the concept of alkenes as taught by Professor James Oponchichiku. Now, the only caution here is that this video is a supplementary material, not an alternate material to what we are doing in class. And then a reminder here is that this video is being made by the HESA Academic Board. And so if you have any issue at all, feel free to contact any member of the HESA Academic Board. Thank you very much. Now, because we have had prior exposure to alkenes discussion when we're talking about alkenes, right? We will not start from the basics again. Now we are starting from the nomenclature of alkenes, which even has a lot of similarity to alkenes, right? Now, the only revision that we can do on alkenes as of now, we'll talk about a lot of things, the reaction, the synthesis, and all, right? The properties. Yes, but the only reminder that we have to have at this point is that alkenes have this characteristic structural feature, C double bond C. And so if you see any organic compound with C double bond C, you should suspect, or you should suspect that that compound is what is possibly an alkene. Now, I am saying that with caution because there are compounds with C double bond C which are not alkenes anyways, right? Yes. And benzene is not an alkene. That is some of the evidence suggested by Kikuli, which we are not even talking about in this discussion. Good. So what we have to take note of is that when you see C double bond C in any organic compound, then we are suspecting that that compound is possibly an alkene, right? Good. This is a structural feature of alkene, the functional group alkene. Good. Now let's delve into the nomenclature. So respect to the nomenclature, this is what we are looking at. Good. Now we are saying that replace the base name of the longest chain that contains the double bond from in to in. Now the same thing. When we have the compound, we will number the longest chain. Depending on the number of carbons, we can name it, meet it. But for alkenes, we don't even have methane. So we start from the 2, carbon number 2, because we have to necessarily have C double bond C, have to get at least 2 carbons, right? So if it's 2 is it, if it's 3 is prop, you understand? So it goes on and on, just as we have in alkenes. Just that after numbering the longest chain, instead of ending with ene as in propane, we end with ENE. That is propene. And so we have something like propene instead of propane. Very simple. That the next rule is saying that number the chain so as to include both carbon atoms of the double bond and begin numbering at the end of the chain nearer to the double bond. So this is a very simple rule. Now we are saying that when we are naming alkenes, the carbons of priority are the carbons that bear the double bond. And so when you are numbering the longest chain, it should always include the 2 carbons which have the double bond. Very simple. The next rule is that now if you are doing that, also make sure that the lowest numbers are attributed to the carbons that have the double bonds. And so you number from an n such that you give the lowest numbers to the carbons that bear the double bond. So if you look at the 2 examples that we have here, the first 2 examples, 1 butene. Now we number, we can choose to number from here, or we can choose to number from here. If you number from here, this carbon that's involved in the double bond has number 1. Then number 2, number 3, number 4. Right now, if you choose the number from here, this is number 1, number 2, number 3, number 4. And so per this rule, now you realize that if you number from here, the carbon in the double bond has number 1. If you number from here, carbon in the double bond has number 3. That is the first carbon has number 3. And so we will not use this numbering. We will use the first numbering instead. That is what we are saying, that you always number such that you would have the lowest number and being attributed to the one that have the carbon that have the double bond. Very simple. Now, because we have 4 carbon here, we would have butane. Butane corresponds to butane, but because in alkene we have a butane, right? Now, the one here is showing the position where the double bond is. So we have 1 butane because the double bond occurs on the carbon 1. Very simple, between carbon 1 and carbon 2, right? Very simple. Now, 1 butane can also be written as but. 1 in. Now we know that between letters and numbers we put a dash, and then between numbers we put a comma. Very simple and basic too. And so when you come to the second example, it's the same thing. We can number from here, we can number from here. But then when you number from this side, that is when you give the least number to the carbons involved in the double bond. So we start from here. 1, 2, 3, 4, 5, 6. Now that is hexene, right? Now it is 2-hexene because on position 2, the double bond comes. You understand? Very simple. Now let's move on. All right, so the next example, okay, there's another rule that I didn't read. Indicate the location of the substituent group by numbering the carbon atoms to which they are attached to. So this example, if I'm using that as a illustration, we have this number 1, number 2, number 3, number 4. Right, okay, let me change the ink. Yes, so number 1, number 2, number 3, number 4. Now 4 is butene, right? It's 1 butene because the carbon 1 bears the double bond, right? Now on position 3, there's a methyl group, so 3 methyl 1 butene. Very simple. Now this one, you start numbering from here. You always start numbering from the end of the chain. That gives the lowest numbers to the carbons in the double bond, right? To the carbons in the double bond. Now, so this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6, right? So we get 6. 6 is hexene. Now, the double bond occurs on carbon 1. And so we have 1 hexene. Now, at position 3, we have a propyl group here, right? 3 carbons, propane, propyl, a substituent, right? And then on carbon 6, we have a bromine group here, so bromo, right? Now, the arrangement here is because of alphabetical order. So 6 come before, the bromo comes before the propyl because of alphabetical order. Very simple. So all in all, we have 6 bromo, 3 propyl, 1 hexene. Very simple. Very simple. Good. Now let's move on. There are a few other rules that we have to talk about. So alkenes are substituents acceptable in the IUPAC system, the alkenyl groups. So now alkenes can also act as substituents. Now these are the acceptable ones that we have in the IUPAC system, right? Very common ones that you meet, which you have to know. These ones you have to know them, and that is it. You have to know them. So we have vinyl. Vinyl is like C H2 double bond CH acting as a substituent, right? Then we have allele. Allele is just like the vinyl, but it has another methylene group before it acts as substituent. You understand? So 3 carbons. Then we have the isopropenyl. Now the isopropenyl is like a branch, like an iso group, isopropane. I mean, if you understand your chemistry, you understand that this is from isopropane, but we have an alkene group here. And so instead of it being isopropanol, it's isopropenol because now this is isopropane. I mean, just so I give the benefit of the doubt, this is isopropane, right? So this is iso, right? Now iso, okay, as a substituent. So this on a normal day, let me draw it in full CH3, CH3, and there's an H here, right? So if this is a substituent, this would have been called isopropanol. Isopropanol is the same as 1 methyl ethyl. Very simple, right? Yes. But then now the difference is that there's a double bond here. And so instead of it being called isopropanol, we have isopropanol, right? These ones you have to know. So yeah, if you know them, it becomes very simple if I ask you to draw isopropanol chloride, right? Yes, so that's for that. That's for that. Next up. So isomerism. Now we are saying that it is similar to alkenes. Now we use the term cis, that is denoted by Z, and trans, which is denoted by E, to describe the configuration of the double bond. Now, if we talk about cis, which is the Z configuration, we are saying that the two groups of priority are on the same plane, or they are in the same plane, or they are on the same side of the double bond. So let me illustrate here, very simple. Now, if we talk about cis, this is the double bond, right? Now, if we say it is in a cis configuration, this is the plane. And so whether both of them are on the same side, on the same side, on the same side, or on the same side. So whether both of them are directed towards here, right? Or both of them are directed towards here, or both of them are directed. So to make it very simple, now we look at the two carbons involved. This will make it very simple. Now, all carbon atoms will have the probability of forming 4 bonds. So that is the 4 bonds that I've shown. Now, we divide it here. So if the groups of priority are all facing forward, like here, like one is here and then one is here, then it is cis, right? Z configuration. If they are both here too, it is still cis, right? Yes, the Z configuration. Now, it is only trans when they are in the opposite configuration. So C double bond C. Now, there's one here and then there's one here. So they are facing directly opposite of each other. Or there's one here and then there's one here, right? So if it's like this or like this, that is when we have the trans configuration, right? Let me change the ink and draw the trans again. So when we talk about the trans like this, we are looking at the groups of priority being like this. Either one is here and one is here, right? Or let me change the color again. One is here and one is here. So from here to here is trans, from here to here is trans, right? Good. So that is trans configuration. Let's move on. We'll get a lot of examples so that we can understand this concept. So trans is denoted by E, right? So any compound that starts with E, especially in alkene, the case of alkene, it means it's denoting trans configuration, right? So cis and trans designation, the stereochemistry of alkene is unambiguous only when applied to di-substituted alkene. So if we have a di-substituted alkene, and we have examples down there that I will use, it's very simple for you to differentiate di-substituted alkene. Let me get one. Yes, this one. Now, this is a typical example of a di-substituted alkene, this one, right? It's very easy to predict. Now, the groups of priority are the ones in red, right? Now you realize that they are on the same plane. So this is cis. That is why we have the Z here or the cis here, right? Very simple. Now, if it's like this, the groups of priority are here. And so you realize that they are directly opposite each other like this. And so this is trans, right? So if we have a di-substituted alkene, it is very easy for you to predict. Now, the conditions become a little bit difficult if they are not di-substituted by it more. So let's look at the next statement that we have here. We are saying that if the alkene is tri-substituted or tetra-substituted, cis and trans are either ambiguous or do not apply at all. So you can get examples where you cannot apply cis and trans, and you can get examples where it is just ambiguous, but you have to figure it out. Now, in case of a lot of substitutions like this is tri-substituted, right? Now, there are criteria for judging which groups are of priority. We use the atomic numbers. And so if you take the example, this one as an example, now we take each carbon at a time. And so if you take the first carbon in a double bond, in no particular order, right? If I'm supposed to actually number, this is carbon 1, this is carbon 2. Now, this is carbon 1 because always when you are choosing the numbering, you number such that the total number that you get for the substituent, right, will give you a very low number. Now, this is not really part of the concept, but let me explain it in this. If I number this 1 and this 2, the substituent would be 1, 1, 2. This is a substituent, this is a substituent, this is a substituent. We don't name the hydrogen as a substituent, right? Good. So 1, 1, 2 will give me 4. That's the addition. Now, if I put the 1 here, if I name it the other way around, so this is number 1 and this is number 2. Now, what I will have is that I would have 1 bromo, then I will have 2 chloro, 2 fluorine in no particular order. Now this would add up to give me 5. I wouldn't want to choose the 5. I would always want to choose the 4. That is why I number from here and then go here. You understand? So very simple chemistry principle. Very simple chemistry principle. This is carbon 1. This is carbon 2. If you take carbon 1, you ask yourself which of the groups on the carbon is of higher priority. We use the atomic numbers. So then we talk about the atomic number of chlorine, which is 17, atomic number of fluorine, which is 9. So definitely chlorine will have a higher priority. Now, if you take the second carbon, which is carbon 2, right, we ask ourselves which of them have higher priority. Hydrogen is atomic number 1. Always is actually very least because it's just 1. That is the lowest atomic number you can actually think of in terms of the elements on the periodic table. Yes, and then the bromine is of higher priority necessarily. Now, we'll compare the 2 atoms of priority. Now, are they on the same plane or they are at different planes, on different planes? Now, they are all pointing towards the same direction. They are here, right? They are on the same plane. So this is cis. This one is cis. And this one is a little bit ambiguous, not straightforward as the other one that we just solved, right? So very simple. Once you get the concept, all the things are very simple. But the other example that we solve, so priority is assigned based on atomic number. Bromine is 35, our rank, chlorine. So in this example, they are just showing us how bromine would outrank chlorine if we, so chlorine and then fluorine, right? Now, fluorine is 9, chlorine is 17. And so you realize that chlorine is of higher probability. Bromine and hydrogen, obviously, bromine is of higher priority, right? So this one here is cis because they are on the same plane. They occur at the same side, right? So that is it. They occur at the same side, so on the same plane. If I put the plane like this, the 2 groups of priority are on the same side. Now, if you look at this, if you put a plane here, they are on opposite sides of the plane, right? And so this becomes trans. This becomes trans, right? If you even put a plane here, they are on opposite sides of the plane, and so it's trans. Very simple. The next example we have solved, so we wouldn't really worry much about it. That is all. So that is all about cis and trans. Now, cis and trans would bring about stability issues in the alkene. So for the same alkene with the same substitution, right? Now, if it is cis, the idea is that the bulky groups will repel each other, so the stability is low. So cis reduces stability, but trans is relatively more stable because of the reduction in the repulsion. Now, the repulsion that we are talking about here is you can put it as a steric hindrance, that is the repulsion between the bulky groups or van der Waals string. The alkyl groups are bulky. They will repel each other because of the van der Waals string, you understand? The bulkiness is a different principle from the van der Waals string, actually. Yes, the van der Waals string is the main thing that accounts for this one. But the steric hindrance is also a very important concept that we can talk about in this discussion, right? Yeah, so bear in mind that even though we are talking about the van der Waals string, it is related to the steric hindrance, very related. So even if you're explaining this and you use steric hindrance, nobody can mark you down. Very simple, right? Good. Very simple. And so because we are looking at the fact that the cis is less stable, you see these 2 compounds are both disubstituted. Very simple, right? But then we are saying that in terms of stability, the trans here is more stable. The trans here is more stable than the cis because of the repulsion between these 2 bulky groups. Very simple, right? Good. Let's move on. Now, the other thing that we have to take note of is we had the first one, which is the most stable. Now, it had the groups on 1 carbon. It had the groups on 1 carbon. Now, if you have this example for you to apply the cis and trans, it is not possible because it's ambiguous. This one is very ambiguous, but this can still come, right? It's ambiguous, so you cannot really apply the cis and trans rule here, right? Good. Then the last one, you cannot apply cis and trans rule there because it's also very, very ambiguous, right? Because of the zero substitution at the other on the other carbons. Very simple. That is not what we are talking about here anyways. Good. Now, the next concept that we have to learn is how to synthesize alkenes. How to synthesize alkenes. Very important concept. How to synthesize alkene. The first method that we have here is elimination reaction. Via elimination reaction. Now, we have dehydrohalogenation of alkyl halides. Very simple concept. The name even gives it away because we are removing a hydrogen and a halogen, right, from an alkyl halide. I mean, an alkyl halide will obviously have a halogen, alkyl groups attached to a halogen, right? To remove a hydrogen, then remove an adjacent halogen, and then we form an unsaturation. So that is what the reaction here portrays. That we have this compound here, it's an alkene, sorry, an alkyl halide, right? Now, we'll lose this X here, and then we'll lose this H here. It will form HX as a side product. Now, this reaction will be assisted by a base. We need to get a very strong base. The base, by the mechanism here, is supposed to remove the hydrogen, right? It's supposed to remove the hydrogen. Now, it will remove the hydrogen as a proton so that the electrons here can be donated here, right? To form the unsaturation that we have here. Very simple. Now, this is the net reaction that in the presence of a base, a very strong base, you can have you forming an alkene from an alkyl halide, right? This is the alkene formed. Now, the reaction is by E2. Now, E2 means that we don't form any carbocation intermediate, right? There's no carbocation intermediate form. It's just a one-step reaction, right? And so there's time that the X is being moved, that is the halogen, which is a good living group, being removed. At that same point, the base is also what? The base is also removing the hydrogen here as a proton, as H plus, so that the electrons here can now be shared by this carbon and then this adjacent carbon, which is losing the halogen, because the halogen here goes away with the electron. That is why it is negative. You understand? And so the halogen going away with the electrons will make this carbon electron deficient. The base will come and remove this hydrogen such that the electrons here will be shared between the beta carbon and the alpha carbon, right? Very simple. Now, the alpha and beta distribution, the alpha carbon is the one that bears the halogen. The beta is the adjacent one. Very simple, right? Good. So that is the mechanism of action here. Is an E2 mechanism, right? Very simple to demonstrate. Now, we are seeing that secondary or tertiary alkyl halides, bases such as alkoxide ion and then polar solvent. So the conditions we need, the alkyl halide we need is either a secondary or a tertiary alkyl halide. Now, the base we need is an alkoxide. A very potent alkoxide is tetbutoxide. Tetbutoxide, very, very potent alkoxide, right? Alkoxide is an alcohol that has lost a hydrogen, right? Alcohol that has lost a hydrogen as a proton. So you can get a lot of the example. And then usually they are very, very strong bases, right? And then we need a polar solvent like an alcohol as a medium for the reaction to occur. Now, this reaction involves the application of the Z-Tefts rule. We'll talk about the Z-Tefts rule. It means that this reaction is reduce selective. That is, we will sometimes get more than one product. One of the products will be a major product and the other product will be a minor product, right? Now, the summary of the Z-Tefts rule is the poor will get poorer, right? So I'll talk about it later in the discussion. This one, let's just move on. The next way of producing producing alkene is dehydration of alcohols, right? So we are saying that most alcohols, when heated with a strong acid, produce alkenes with a loss of water. Elimination reaction favored at higher temperatures. So this reaction is basically an elimination reaction. We are still under elimination reactions. Now, the condition we need here is heat and an acid. We need a strong acid, and then we need heat to dehydrate the alcohol, right? There's an interesting reaction. We'll talk about how interesting it is when we go down there, right? It goes back and forth like that. And so what happened here is that when we add the acid and then we heat it, the OH will be lost. The hydrogen on the adjacent atom would also be lost, and then it will form a side product, which is water. Then there will be an unsaturation between the two carbons, which are adjacent to form our alkenes. Very simple concept. Very, very simple concept. Now, commonly used acids are Bronsted Lowry acids, such as sulfuric acid and phosphoric acid. Lowest acid, such as alumina, could also be used. So let's take note of these reagents. Now, dehydration of alcohols. Primary alcohols are most difficult to dehydrate. The simple reason here is that this reaction, the mechanism of reaction, involves the formation of a carbocation, right? Involves the formation of a carbocation. Now, the primary carbocations are not stable, and there's no reaction which will lead to a not stable intermediate. Because the idea is that reactions occur necessarily to form more stable products. That is why they react. And so if it's going to form something which is highly unstable, it is very difficult to go to that state. Right? So because it involves the formation of carbocation. Now, if it's secondary carbocations are relatively more stable compared to primary, right? Yes, and so you realize that the dehydration process is easier, and so they are saying that it requires milder conditions, right? Now, if we talk about tertiary, you require extremely milder conditions because tertiary carbocations are relatively the most stable, right, between primary, secondary, and tertiary. And so that is what we have. And then sometimes we don't get these statements, but the conditions to which the reaction is responding to expose the reaction as being a very difficult reaction. So if you look at this one, the first one, which involves a primary alcohol being turned to alkene, right, ethanol. Now look at the point. We need a concentrated H2SO4, and then the temperature is 180 degrees Celsius. Now, in the case of the secondary, right, the cyclohexanol, we need 85% H3PO4, right? And then the temperature range is lower than what we have in the case of the primary. Now, if you look at the tertiary, right, we need just 20% of aqueous sulfuric acid and then 85 degrees. So if you compare to the 180 degree, realize that this is very mild condition, but you still get your alkene anyways, right? And then I said the idea behind it is because we are forming a carbocation. And then respect to carbocations, tertiary carbocations are the most stable, followed by secondary carbocations, followed by primary carbocations. That is why, with respect to relative ease of dehydration, tertiary alcohols are easier to dehydrate, followed by secondary alcohol, with primary alcohols being the most difficult to dehydrate because it leads to the formation of a primary carbocation, which is very, very unstable, right? Good. So let's find ourselves. Yes, we are here. Very important point to take note of. Now, the mechanism of dehydration. This is a very simple mechanism, interesting too, right? Now, the first one is that the electrons on the oxygen in the OH group, right, of the alcohol will attack a proton. It will attack a hydrogen in the acid, right? Now, when it attacks the hydrogen in the acid here is H3O plus. When it attacks it, now the bond between the hydrogen in the acid and then oxygen here is broken onto the oxygen. Now, when this occurs, you realize that the oxygen here is electron deficient. So the electrons here will neutralize the positive charge. So we'll get water, right? Normal H2O. But then the electron being donated to the hydrogen here will make us form a new bond between the hydrogen and the oxygen here, right? Now, because the oxygen has formed an extra bond by donating the electron, we have a positive charge. On a normal, the oxygen forms 2 bonds, but now it's forming 3. So we have a positive charge here. Now, this group that we have formed, the protonated alcohol, which is the first step, the protonation, right? The protonation of the alcohol, which is the first step, will make us form H2O in the compound. Now, H2O is one of the best living groups. And so what it will do is that it will live on its own. Now, when it is living, it would break off the. So now in the second step, what is happening here is that we have the bond here, the bond being shared here, break onto the oxygen, the O plus. Now that will neutralize the O plus again, and then you form normal water side product. Now this is when you form the carbocation. This is the slowest step, and this is the rate determinant step in the whole reaction, right? So we lead to the formation of the carbocation. Now, always when a carbocation is formed, the carbocation will ask itself a question or act in a way. It's very important. When you miss that question, you miss a lot of reactions, right? Now, always there can be a hydride or an alkyl shift. We'll talk about that more. But then even though this one will not apply in this example, always we ask ourselves so that we don't forget when we have to ask ourselves, right? That's would this particular carbocation that are formed, is it the most stable carbocation that I can get? Now, this is tertiary carbocation that we have formed here. So by automation, we just know it's a very stable carbocation, so we can proceed with the next step. But then should we form a primary or secondary carbocation? Now, the idea is that we can form a more stable one. And so when the answer to that question is that we can form a more stable one, then the next question is that can there be a shift in a single hydrogen or a shift in a single alkyl group to give a more stable carbocation? So 2 questions. The first question the compound will ask itself is that, is this the most stable state I can assume? If that is the most stable state it can assume, fine. It would continue with the reaction. If there can be a 1-2 shift, that is just an adjacent shift, one shift to form a more stable carbocation, then what will happen is that there will be that shift, there will be that rearrangement, right? Yes. And so there are cases which we'll talk about. There are cases where we would produce a secondary carbocation by the loss of the good living group, the water, right? Now, there can be a shift to form a tertiary, and so that shift will occur before we can actually come and form our final product. In this case, there will not be any shift because we have formed tertiary. So when we get there, we'll talk more about it, right? So the next step is very simple. Now, the next good thing about this one is that the carbocation, all the groups around it are symmetrical. I am mentioning these conditions so that we don't miss. All these are similar. The carbocation has CH3, CH3, CH3 surrounding it. And so it is symmetrical. Because it is symmetrical, I mean, there's no issue with this one. There is no issue with this one. No matter where we remove the proton, we'll get the same product. Now, there's this thing that will happen, that when the carbocation is formed, this next step is actually to remove a hydrogen from the adjacent carbon to the carbocation, right? To form an alkene, a double bond, an unsaturation. Now, the CH3 that the adjacent carbon can be any of them. So it can be this one, it can be this one, or it can be this one. Because these 3 groups are the same, we can just remove it from any of them because they will give us the same product anyways, right? Good. And so we just isolated this one. It's CH3, so we just isolated this hydrogen because of example. And then the water came to take a hydrogen. So electrons, arrow move from electrons, right? So electrons, the arrow here shows where the electrons are traveling to. The electrons will move from here to here, come and take this hydrogen. The hydrogen will be lost as a proton, right? So the bond being shared there will break onto the carbocation to form the unsaturation between this carbon and this carbon. Very simple. That is what we have here. The next reaction, I will demonstrate it, right? Good. So that's for that. Now we have our single product 2-methyl-propene. This is a very simple example and straightforward. Now, this is the example I am interested in. And for this example, I will share a white screen and then I would describe it. because this example involves a shift. Now, if you are not very professional and then you want to do this with your eyes, you get it wrong, right? But then when I teach the mechanism and then now you understand the mechanism, it is very easy to do this straight up, right? Now we are forming two products. It's stereo selective, right? It's very stereo selective, radio selective. And so we are forming two. One of them is major, one of them is minor. Now I will use the Z-Tep's rule to explain why one of them is major and minor after this demonstration. Very simple, right? It's a very mild condition because it's secondary alcohol. It's a secondary alcohol, right? Yeah, so very simple. Now let me share my screen. The compound is 3,3-dimethyl 2-butanol. 3,3-dimethyl 2-butanol. So we have 3,3-dimethyl 3,3-dimethyl 2-butanol. Now, always when I'm drawing, I like to start from the parent name, right? So butanol is 4 carbons, 1, 2, 3, 4. Now 2-butanol, that is on position 2. Then we have the OH on position 2. There's OH here. Very simple. That is how I do my work. Now there's 3,3-dimethyl. So on position 3 we have methyl group here, methyl group here, right? So this is my carbon 1. Now let me add up. This is CH, and this one doesn't have H again, but this is CH3. So this is my compound. I've filled in with the hydrogens because I know all carbons will form 4 bonds, right? Very simple. Now, the first step, usually there's an acid, but then we use H3O plus. H3O plus because the acid usually protonates water, and then water, protonated water is H3O plus. This is the structure of H3O plus. So that is what we use in a lot of the reaction, right? H3O plus, this one, right? Good. So that is what I would use here. Now, the first step, let me draw my H3O plus here. H3O plus. Always the first step is that this one, the electrons on the oxygen in the hydroxyl group will attack the hydrogen here, right? Now, when it attacks it, the electrons here will break onto this, the oxygen. So we form a side product of water, H2O, from this one, right? The plus will be neutralized. Then from this one, we'll come and form a compound like this, CH3. Everything in the compound is the same. The only difference is where the reaction is occurring. So I'm drawing the same thing, CH3. But then on this side now, I will have O bonded to hydrogen here and bonded to another hydrogen. It has electron and it has a plus. This is so because, all right, so we understand this one because it has now taken an extra hydrogen, and then it will have a plus sign because oxygen would have to form 2 bonds, but now because it has donated the electron to a hydrogen, a proton now is forming 3 bonds, so it has a plus, right? Very simple. Now, the next step is that this group formed the H2O class here. It's a good leaving group, and so it will leave on its own. Now, when it leaves with the electrons on it, right? And so the whole of this group will leave. Now, the oxygen here, the electrons here break onto this oxygen. Let's be very mindful. Always, you should know where the arrows are moving from to where the arrows are moving to. It's breaking just onto this oxygen. And so the side product will still have water as a side product from this, from what's happening up here, right? And then this part of the compound will be this, CH3. Now the compound has not changed. Every part of the compound is the same. Every part of the compound is the same, right? Now, the only difference is the part that has lost it. So this carbon, the carbon 2. Now there'll be a plus here because the group here has left and then taken the electrons away. Now this carbocation form is a secondary carbocation. So this is the point where the carbocation will ask itself, can there be a shift, a single shift, a 1-2 shift, such that I can form a more stable carbocation? Very important question. Very important question. So either we are looking at an alkyl shift or a hydride shift. Now, the truth is that if you analyze this compound very well, I can shift this group, this alkyl group here. Now, if I shift it here, the alkyl group will be here, right? The plus sign will move here. If I put the plus sign here, I get a tertiary carbocation. And tertiary carbocations are more stable than primary and secondary carbocations. So now the answer in this case is yes, I can undergo a skeletal rearrangement to form a more stable carbocation. So that is exactly what the compound will do. Because all the compounds would want to go to form a more stable state. Now look at the arrow here. The arrow here has changed. This is not a reaction. This is like a resonance, right? This is like an alternate form of the reaction, a rearrangement, skeletal rearrangement. So we use this arrow. Right? And so we have this now CH3. Now what is happening here is that the CH3 is moving to this carbon, and then the plus sign will come and be on this one. So C, the CH3 here, the C. Now this C will now have CH3 because he has moved it, right? Now there will be the hydrogen, and then there will be the CH3. Very simple. Now the plus sign will come here. We have now formed a tertiary carbocation, which is more stable. Now from here, the other reactions can occur. Now the next step, I mentioned emphatically that the condition is that we will look at the carbocation and then we'll check the surrounding. The alkene is supposed to be formed between the carbocation and the adjacent carbon atom. Now let's look at the adjacent carbon atoms. This is adjacent. This carbon here is adjacent, right? This carbon here is adjacent. Now, this carbon here is also adjacent. This carbon here, all these ones are also adjacent. But the truth is that this one and this one are the same, right? But then this one is different. And so this will inform us that we will form two products. If I remove hydrogen from here or from here, I'm getting the same product because it's the same environment. But if I remove a hydrogen from here, I'm getting a totally different product. And so I'll get a product by removing a hydrogen. Now look at this carbon. There are only 3 carbons which are adjacent to it. Is this one, and then is this one. This one has a hydrogen. This has a hydrogen. This has a. Is that the 2 of these are the same. This is different. This is not part because it's not adjacent to this one. It's not directly attached to it. This is not part because it's not directly attached. We are looking at the carbon directly attached to the carbocation. And so in the next step, let me write on the next page. In the next step, this is what will happen. Let me draw the compound again. This is what we have. We have CH3, C plus, CH3, CH, CH3, CH3. Very simple. Now, this is what we have. Now we have to form the products, right, from the adjacent. Now, because these two are the same, I'll just isolate one of the hydrogens, right? So instead of making it 3 hydrogens here, I am coming to make it 2, and then I'll bring 1 hydrogen here. That is because it's about to undergo a reaction, not because of anything, just because it's about to undergo a reaction. So I just want to isolate one to make it very simple. Now, instead of making this one here, the CH, I'll try and just isolate it. So I'll bring this H here, right? Now, in the first instance, the 2 will not be removed at the same time. In the first instance, right, the water coming in is the water that will come and remove it. This is water, right? The water can come and then remove this proton. If you remove this proton, the electron here will be shared with this. So it will be shared between this carbon and then this carbon. So the double bond will be formed here. We can call this product. If that happens, the product A will be this. Product A will be CH2 double bond C, CH3, then there will be CH, then there will be CH3 here, then there will be CH3. Note that I brought this hydrogen as if nothing has happened to it, because in the first instance, nothing actually happened to it. Now, the water can also decide to come and take this one, right? Now, if it takes this one, the double bond will be formed between this carbon and this carbon. And so in that case, the product B would be now I'll maintain this hydrogen as if nothing has happened to it, because if we are looking at part B, nothing has happened to this hydrogen. So there will be CH3, then this is CH3, then there will be a double bond here, C, and there's CH3 here, and there's CH3 here. This is product B. Now, this mechanism has to be rehearsed. If you just watch it and then go out, you might not be able to reproduce it. You have to rehearse it, practice over and over again. Now, when we finalize on the product, we are not done. We have to now determine which one is major or minor. Now, we use the Z-test rule. I've already mentioned that the Z-test rule says that the poor will be poorer. Very simple. And so we are saying that now when we are at a crossroad and then we have to choose between two products, the major product would be gotten from the step where we removed the hydrogen from the one that had a lower number of hydrogen. I'll state it in two ways. This is the layman view, that when we remove the hydrogen that had a lower number of hydrogen, the product that resulted from it is the major product. And so look at this. In the A section, if we are looking at part A, right? Now, this one has 3 hydrogens, and then we removed one of them to get the first product A. Now, if we are looking at part B, this carbon here has just one of them, right? Just had one, and then we removed it to form product B. And so the one that had fewer hydrogens, and then we still took away the hydrogen, the product from that one is the major product. And so B is the major product. B is the major product. And the one that had more hydrogens, right? And then we took hydrogens from it, right? Now becomes what? Now becomes the minor product. The poor gets poorer. The rich gets richer is Markovnikov. The poor gets poorer is what? Z-tips. Now, this is the idea. Now, that is not the chemistry. The actual chemistry is that now, if you substitute, or if you what do we call it? Eliminate from the carbon that has a lower number of hydrogen, you increase the number of substitution. You increase the number of substitution. Now, if you increase the number of substitution, you increase the stability. Now, if you increase the stability, then you get the major product, because the major product should be a more stable product. So let's look at these two products that we have here. Now, this carbon here, there are 2 carbons which are involved in the double bond. This is, let's say, this is carbon 1, and this is carbon 2. It's not in any particular order. If I'm naming it, well, this is carbon 1, this is carbon 2, actually. Right, carbon 1, carbon 2. Now, if you look at carbon 1, it has 2 hydrogens attached to it and the double bond. It is not substituted. This is unsubstituted. If you look at carbon 2, it has 2 substitution, because this is bonded to carbon and this is bonded to 2. This is disubstituted. Fine. Now, if you come to B, look at the carbons involved in the double bond. It is this carbon and then this carbon. So this can be A, this can be B, right? Now, if you look at the first carbon, it is disubstituted. It has this substitution and this substitution, right? Now, if you look at carbon B, it has this substitution and it has this substitution. It's also disubstituted. So this is a tetrasubstituted product. And then the Z-test rule in actual chemistry is actually telling us that we should choose so that we get more substitution, because more substitution will give us a major product. So that is actually the Z-test rule. So me saying that the poor get poorer is not the Z-test rule, but it's a way to easily understand the Z-test rule. You understand? But the actual chemistry is that if you apply the concept of the poor becoming poorer, you lead to a product which is more substituted. And then the more substitution here will lead to a more stable product. And the more stable product will now become the major product, Zatev. So that is that for that. Let's go back to our slides. Okay. So now we are here. Back to the slides. Now the mechanism I talked about. So the two products that were gotten, the minor product, this product A from my discussion, and this is product B, right? The disubstituted. Very simple. Now there's a mechanism we can follow this one, right? This is the transition state where we had the methyl shift, which is an example of an alkyl shift, right? This is a methyl shift, right? Now the Zatev, the formation of the more stable alkene is favored. That is the Zatev's rule. Very simple, right? Now the next way forming alkene is by debromination of vicinal dibromide. So vicinal is 1,2, right? So 1,2, like in the same vicinity. So 1,2, 1,2, right? Carbon 1, carbon 2. Then we have bromine, right? So dibromide, vicinal dibromide. Now debromination is when we remove the two bromine groups. Now what I want us to take note of here is the reagents. We have another reaction in alkynes, and the difference will only be the reagents. And so we take note of the reagents here. Now the first reagent they use here is sodium iodide in the presence of acetone. The side products are the same. Sodium bromide will be the same if we use sodium iodide. The sodium is the metal here. The iodine is the same. You understand? Yes. Now this is a very important test for vicinal dibromide too, because of the iodine that is precipitated, because we can test for the iodine with touch. Very simple. We can also use zinc. So the zinc metal in the presence of either we are using acetic acid or ethanol, right? It can also give us. Now the side product here once again is fixed, right? It's fixed. This one there is fixed, right? Good. And then the thing that you have to know if you get this reaction is that you will lose the two bromines here, and there will be a double bond formed here. So the two sigma bonds here are lost, and then we have a pi bond forming between these two. Now reactions of alkenes. So we are done with the synthesis. Now we are looking at the different reactions that alkenes will undergo. The first reaction. Now this is the major reaction that alkenes undergo. Very characteristic of alkenes. That is addition reaction, right? And so if you hear alkenes, the first reaction that will come into your head, right, is addition. It's actually for all unsaturated hydrocarbons. Addition reaction is the principal reaction of alkenes, right? Now, we have to understand how the addition reaction, right? So addition reaction will lead to the conversion of one pi bond to two sigma bonds, right? So conversion of one pi bond and one sigma bond to two sigma bonds. So what we have here, always double bond, the third bond here in no particular order is the sigma bond. The second one is the pi bond. The pi bond is weak. So usually if we have the two, usually the pi bond is the one that will break, right? Now the bond between the X and the Y here is sigma bond, right? And so you realize that the pi bond here will break, the sigma bond here will break, and then now we would have two different sigma bonds formed. That is a typical addition reaction form, right? This is just for understanding sake, right? Now the electrons in pi bond are susceptible to electrophiles, right? They are susceptible to electrophile because they are electron rich. The pi bond is electron rich, so electrophiles can attack it. Very simple. Now the first addition reaction we'll talk about is addition of hydrogen halides to alkenes. Now we are seeing the addition of hydrogen halides to alkenes occur rapidly in solvents such as pentane, chloroformacetic acid, and then benzene, the normal organic solvents that we know, right? Now this is a general form of a hydrogen halide, HX. So the X can be any of the halogens that we can think of, right? Now what will happen here is that this is symmetrical. Now, if it's symmetrical, we don't have any issue. And so, mind you, the example becomes tougher along the line. But the first example here, what I want to draw your mind here, it is so easy because the compound here is symmetrical. If you divide or bring a plane between the C double bonds here, on this side we have the same structure, and on this side we have the same structure. You understand? And so what will happen here is that the double bond will break, right? The pi bond will break, yes, specifically, and then the carbon here will be attached to H, the carbon here will be attached to X in no particular order, right? It can also be interchanged. Now, the example here is this one. This is also symmetrical. If I divide this, you realize that the group here is the same as the group here. It is all monosubstituted. And so the same environment. Now, if you add HBr, right, in the presence of the chloroform, you realize that you get the H can be attached here. That's the pi bond will break, and the Br can be attached here. No particular order. So that is what we have here, right? 3-bromohexane in no particular order. Now the example changes depending on the example we are looking at, right? Yes, so the concept will change a little bit as we go along, but this is very simple. The mechanism is very simple. Now, I mentioned that the pi bond is electron rich. And so the electrons in the pi bond will attack the electron deficient. You see, this bond here is polar because the X is more electronegative than hydrogen. So now, even in this normal state, the hydrogen here has a partial positive charge, and then the halogen here has a partial negative charge because of high electronegativity. So the electron-rich pi bond will attack this electron-deficient hydrogen to donate electrons to it, right? And that will make us form this new bond between this carbon and then this hydrogen, right? Now, when the bond is being formed, the halogen would break off and take the electrons away. So this electron breaks in a sense to this halogen, which becomes X minus. Very simple. Now we form a carbocation, right? That is a slow step. Always the formation of carbocation is a redeterminant step, very, very slow step, right? Then the next one is the coordination. Because you have a plus, that's a carbocation, and then minus in solution, they will coordinate, right? So the halogen will donate electrons to the carbon, the carbocation, to form a new bond, right? That's a very fast reaction. It means the first step is the redeterminant step for the second one. Now, radioselectivity will come in this one when the compound we are talking about is not symmetrical. I've already mentioned it. So if you look at the example at hand now, this compound here is not symmetrical. It is not symmetrical at all, right? And so now we have to apply a principle. This is addition reaction. The principle we apply here is the rich will get richer. The rich will get richer. That is, the major product will be formed when we add the hydrogen to the carbon that already has more hydrogens, right? And so look at this example. Now, the two carbons we are concentrated on is this carbon, which is involved in the double bond, and this carbon, which is involved in the double bond. Now, if I add the HBr, this hydrogen is attached to this one. Because this has more hydrogens already, that is, it's already rich in hydrogen, the major product will be formed when I add an extra hydrogen to this one. That is, the rich will get richer. We understand. And then the Br will be attached to this one. That is what we have here. So the Br is attached to the second carbon and the hydrogen is attached to the first one, right? That gives us the 2-bromobutane, which gives us 80% of the product, the major product. Now, can moving on. So similar example is the same concept of the rich will get richer, right? The rich will get richer. And so you realize that the two things that we are focused on is this carbon and this carbon. Now the hydrogen will be attached here. That's when we break the pi bond, the hydrogen will be attached here, and then the Br will be attached here. That is what we have here, right? It's very simple. Very simple. Now, what we talked about, the rich will get richer is Markovnikov. The poor will get poorer is Zitev's. Very simple principle, right? Now, the rich will get richer is an easier way of getting the concept. But then there's an actual chemical or chemistry understanding behind what we say, which we'll talk about in the next slide. But then the Markovnikov rule states that when an unsymmetrically substituted alkene. Now, I told you that when it's symmetrical, we don't have a problem where the bromine or the halogen or the hydrogen will go because it's symmetrical. But in case it is not symmetrical, that's when the problem will come. That is when the radioselectivity will come in, right? Yes. And so we are saying that when an unsymmetrically substituted alkene reacts with a hydrogen halide, the hydrogen adds to the carbon that has a greater number of hydrogen substance. That's the rich getting richer in essence. And the halogen adds to the carbon that has fewer hydrogen. This one, I don't think you have to chew it. You can understand it, right? That when we are dealing with unsymmetric alkenes, right? Add the hydrogen of the hydrogen halide to the carbon that has a greater number of hydrogen, and then add the halogen to the carbon that has fewer number of hydrogens. Very simple. Now, the reason for Markovnikov rule. The reason for Markovnikov rule. So the first reason, we are seeing that the transition state of the addition reaction involves the formation of carbocation, which I am sure we have seen in the mechanism. Now, the more stable the carbocation is formed, the faster, right? And hence predominant. Now, tertiary carbocations are most favored, followed by secondary, and then primary carbocations do not form appreciably. So this one we have come across before. The reason why we have to talk about Markovnikov is because the transition state involves the formation of what carbocation. And it is when you follow the Markovnikov, that is when you can form a more stable carbocation for the reaction to proceed, right? Good. So that's for that. This is a very simple concept. We have to know the Markovnikov rule, and then we have to understand the reason why the Markovnikov rule is very important. So this is an example to illustrate that when in this case, now look at the first instance is the right one, right? That when we add this hydrogen to this one, the C, these are the two carbons we are considering. If we add the hydrogen here, now the plus sign will form here, right? So that's what we have here. This is a tertiary carbocation, which is very stable. And so the Br can attack it, will form our stable product. This is the actual product. Now, in the next instance, look at what we would have had if we turn it. If we turn it, the hydrogen will be attached to this carbon, right? Now, the plus sign will be on this one. This is a primary carbocation, which is highly not stable. Because it's highly not stable, it will not form, right? So do not occur appreciably. The product is not formed at all, right? So that is the reason why we have the Markovnikov rule, because we understand that the reaction would lead to a transition state that involves carbocation. And it is when we follow the Markovnikov, that's when we can get either a secondary or a tertiary, which is more stable than the primary, which we want to avoid. Now, exceptions to Markovnikov rule. The addition of HBr to alkene in the presence of peroxide occurs in an anti-Markovnikov way. Now, this is an exception. The exception here is very specific. Let's not get confused. Now, the compound we are talking about is necessarily HBr. HBr is not the only hydrogen halide. So there are other hydrogen halide like HCl, HF, and then HI, which are not prone to this exception. That is, if I add HCl in the presence of peroxide, it will act in the Markovnikov way. It is only HBr when we add in the anti-Markovnikov way. Sorry, when we add in the presence of peroxide, that's what will react in the anti-Markovnikov way, right? Very simple. A very, very, very simple concept. So that's a very simple concept that we can take note of. Addition of sulfuric acid to alkenes. Now, the same addition reaction, it's the same as we have in the alkyl halide. It follows Markovnikov rule, right? Yes. Now, this one, the condition is that it should be cold, right? If it's hot and there's water in the medium, you get an alcohol. So if it's sulfuric acid, cold sulfuric acid. So it was stressed here, cold sulfuric acid, cold sulfuric acid. The cold is here. right? So let's take note of that. Very simple. Now, if I'm supposed to run us through the reaction, which is super simple, and we have the alkene. Now, this is sulfuric acid. This is sulfuric acid. This S double bond O, double bond O, OH. So this is sulfuric acid, right? Now, we don't draw the whole structure sometimes in mechanics, even though you can draw this and then show, because the reaction is occurring either here or here, right? Yes, sometimes we condense it. So we condense it to be, condense the whole of this and just show one of the OH if one of them is needed to be shown in a mechanism. So that is what we have here. So we have SO3H OH is the same as the sulfuric acid here, right? Just that we want to isolate this OH to be shown in the reaction mechanism. Very simple. Good. So we have this one. So the alkene, the pi bond will attack the hydrogen here, right? Now the hydrogen will be attached to this one because your base Markovnikov, the one that has more hydrogen, so will be attached here. The carbocation will fall here, right? So we have a secondary carbocation. Now there cannot be any skeletal rearrangement, so we just go ahead and then we add the sulfate group. Now the sulfate group here is this hydrogen sulfate, sorry. So the hydrogen sulfate group here is negatively charged. It will donate its electron to the carbocation to form the alkyl hydrogen sulfate. The alkyl hydrogen sulfate, right? So that is what we have. Now, let's move on. So, if we want to proceed to alcohol, what we have to do is that we have to add water and then heat. And then usually there's water in the medium of the reaction. And so the only thing that we have to add now is heat, right? And so that is why if you don't want to progress to your alcohol, you have to make sure that your sulfuric acid is cold. Because once there's heat and there's water, you will get alcohol. So now we are seeing that in the two-step reaction, if we are converting alkenes to alcohols, first up, we can add sulfuric acid cold, and then it will give us the alkyl hydrogen sulfate. And then we can add water and heat to get our alcohol. Very simple. And then we'll get our sulfuric acid back. The fact that we are producing the sulfuric acid back shows that it is a catalyst in the reaction. The catalyst because it's just speeding up the whole reaction in a way. How we put it in, it came out in the same way. It didn't change because catalysts are not supposed to be changed in the course or at the end of the reaction. Right? They are not supposed to be changed or consumed at the end of the reaction. That is very simple concept. Now, so we are expanding on the same principle. It's the same principle anyway. Acid catalyzed hydration of alcohol, right? Hydration of alkenes, it will still produce alcohol. So we are saying that low molecular weight alcohols can be prepared by acid catalyzed addition of water to an alkene. The acid commonly used are dilute sulfuric acids and phosphoric acid. The reaction is radioselective and obese Markovnikov. We have talked about all these. The formation of primary alcohol is not usually favored because primary alcohols will form a very unstable carbocation, right? Very simple. And so we have examples. The first instance, we have a symmetrical compound. Now it has the acid and then it has water, right? They have not mentioned temperature, but then the idea is that it has a little bit of room temperature. If we have not mentioned temperature, it means it's not cold. It means it's our room temperature, which is sufficiently warm. And so we form the alcohol straight up. Now we don't care about where the OH is, where the hydrogen is, because once attached to the carbon involved in the double bond and it's symmetric, we know we'll get the same product. But in the B, the compound there is not symmetric. It means we have to be careful because we have to apply Markovnikov, right? And so we make sure. Now what we do in essence is that if we are not using the mechanism, we are adding water. Now, water was split into hydrogen and OH, right? And the OH will be attached to one of the carbon. That's after breaking the pi bond. OH will be attached to one, and then H will be attached to the other. So the major product by Markovnikov is when we attach the hydrogen to the one that already has more hydrogens, and then we attach the OH to the one that has what? That has fewer hydrogens. So this is the major product that we have here. Very simple, right? Good. So now we are looking at mechanism, right? Now the same mechanism which we have talked about in the other ones. The pi bond will attack the hydrogen in the acid. The bond will break onto the oxygen to form water, right? Now the plus sign, the hydrogen will be coordinated to this carbon, the first carbon here. It will be coordinated to the first carbon here. And so you realize that the carbocation will fall on this one. Now, it is good it fell on this one because this is a tertiary carbocation, is very stable. Now, water would attack, because water has electron, will attack the carbocation. Now, when water attacks the carbocation, now we would form a water coordination to the carbocation, right? Good. Now, because there's a plus sign and there's water, we have not gotten our alcohol yet. So the next one is that another molecule of water will act as an acid to come and take a proton from here, right? Another molecule of water will act as an acid to come and take a proton from here. So that is what is happening here. We take a proton from here. Now, when we take the proton from here, right, when the proton is being taken from here, the bond between the hydrogen and the oxygen here will break onto this oxygen. Oh, it is very important we note where the bond is breaking onto. Break onto this oxygen to neutralize the positive charge, and then we'll get our alcohol. Right? Good. Once again, the rate determining step is when we are forming the carbocation, right? It's when we are forming the carbocation. This is how the reaction is. And then for every single mechanism, I always advise that we practice it over and over again. Practice this over and over again, right? So that we can become familiar with it. Now, comparison of acid catalyzed hydration of alkenes and dehydration of alcohols. So now when we were talking about the synthesis of alkenes, we realized that we can dehydrate alcohols to form alkenes. Now we are talking about reactions of alkenes, and then we realize that we can hydrate alkenes in the presence of an acid, right? To get an alcohol. So you realize that this reaction is reversible. It can go forward or backwards, right? Because all of them will require acid. Now, the only difference here is that when you increase temperature, what you are doing is that you are heating it. Now, when you heat it, you force it to dehydrate. That is, you lose water. Now, when water is being lost, the equilibrium reaction will shift to the reactant side. That is, in this case, right? It will shift towards our left to produce more of the alkenes. But when you dilute, that's in the next case scenario, when you dilute this reaction, right, that when there's more water, the equilibrium will shift to this direction so that you produce more alcohol. So now the trick here to get the desired product or prevent interconversion is you managing heat and water content. Now, when the water content is very high, that's when it's very dilute, you will shift the equilibrium to the right side just in order to consume more water and form more alcohol. Now, in the same scenario, if you are heating it a lot and you are losing more water, that is, if water is less, you would shift the equilibrium to this side so that you can produce more water because water is being lost, and then you produce more alkene, that the dehydration will occur. Understand? So that is how we can apply our knowledge of equilibrium to even this case that we have here. Very simple. Very simple. Okay. Addition of Br or Cl2. alkenes. Now, there's one characteristic about the halogens that naturally they exist as diatomic molecules. Now, the only trick here is that you have to pay attention to the solvents which is in play. Now, this reaction can occur in a non-nucleophilic solvent like CCl4. In that case, this is the first scenario is what we have. So the first scenario, we have chlorine gas reacting with, this is also a symmetric A. Even if it's not symmetric, you form the same thing, so we don't worry. That's why we have 100% here. Right, so chlorine. Now, what will happen here is that the pi bond will break, and then each of the carbons in the double bond will form a single bond with the chlorine, right? So we have a vicinal chloride. Then the next scenario, we have bromine, same thing. The condition is CCl4. Now we have a vicinal bromide, right? Big bromide, 1,2 bromide, very simple, right? Now this is a test for alkenes, a very important test for alkenes. That is the bromine one, because the alkenes can decolorize bromine. So in a compound, if you want to test for the presence of bromine, bromine is red. That's red-brown. That is what we have here, right? Now, if you add it to the unknown solution and then you realize that it becomes colorless, that is the compound has been able to decolorize bromine. It's either it is an alkene or an alkyne. That's the unsaturation. That's the conclusion that we rise at. That there's an unsaturation in the compound. So it can either be an alkene or alkyne. So very important test for alkene or alkynes. Very important. Let's keep that in mind. If this reaction comes in, they ask us the significance of the reaction. That is the significance of the reaction, right? Now, in the next scenario, the solvent can change. If the solvent is water, like we have X2, that's any of the halogens in water. If the reaction is in water, then we form a halohydrin. And so what will happen is that the halogen will be bonded to one of the carbons, and then the OH would also be bonded to another carbon, right? Very simple. So let's take note of the solvent if we are talking about something like this. The next concept is ozonolysis. Ozonolysis. Now what we have to take note of here is that if you have an alkene in the presence of ozone, you form an ozonide. Ozonide, an important intermediate, very, very important intermediate. Now, it's very important because when you treat ozonide with zinc or acetic acid, you produce carbonyl compound. So it's either you produce an aldehyde or a ketone. Now, this is a condensed form of the reaction, which is very important. So now in the first step, the first reagent that we use the ozone. Now in the second step, we use the zinc in what? In the acetic acid. Now you realize that you are getting two carbonyl compounds, right? Now, very simple. You don't have to know the mechanism and all, but what you have to know is how to draw the product for this one. How to draw the product. So here. We cut it here. Now, the bond will break here. That's the two bonds, the sigma bonds and the pi bonds will break, right? Now, when they break, this one will be double bond O. This one will be double bond O, right? So it's still like the double bond, but each of them is going to be double bond O, double bond O. Now, these sides will not change. These sides will not change. And so in the example that we have down here, if I'm supposed to predict the product, the answer is there already. If I'm supposed to predict the product, you can do it without thinking, because the only thing that we have to know is that we are breaking this one, right? And so this same compound, this C, the H3 here, the CH3 here, right? Double bond O. So that is, I've just broken the side. Now, the next product is this one. That's it. So we just break this one, double bond O, double bond O. That is it. We have gotten the product. This is the same as this one here, and this is the same as this one. Very simple, right? Now, if you have a question like this, and then you don't know the importance of this reagent, you might not be able to predict the product. So something very important for us to take note of. Very simple, right? Good. Next up. Now, the mechanism we can go through, but then the mechanism, we will not be worried with the mechanism, right? But we can still research more and read on the mechanism of ozonolysis. The next one, which is very important to us, is this one: oxidation of alkenes. Now, the oxidation can lead to a lot of products, but this particular first slide is trying to make us oxidize the alkene to produce a glycol. Now, in that case, if we want to produce a glycol, it's an important compound, produce glycol, we use two main reagents. We either use potassium permanganate or osmium tetraoxide. Now, if you are using potassium permanganate is a very powerful oxidizing agent, which has the potential of further oxidizing what we have, which we don't want. And so we subject potassium permanganate to a basic condition and a very cold temperature. Now we are giving it a cold temperature and a basic condition in order to reduce the oxidizing power. There are other references, or in other instances, that is the more accurate way, where we use potassium permanganate in acidic solution or in a very hot, we warm it, right? Higher temperature. Now, we will do that only when we require a very strong oxidizing effect. In that case, you will cleave both the sigma and the pi bonds. You will cleave them and it will fully oxidize them. It will oxidize them to even acids, alkaloic acids. But because we are very intentional about the product we want to produce, the KMNO4 is in a basic solution. That is why we have the OH minus here, right? In the basic solution, and it is cold to make sure that we are utilizing the weak oxidizing power of KMNO4. Now, because KMNO4 is very unreliable, because it's very strong, the best reagent that we can use here is osmium tetraoxide in pyridine. Because the osmium tetraoxide will make sure that we don't have further oxidation and then we have a higher yield. So I've talked about disadvantage of KMNO4 and I've talked about advantage of osmium. Very important that we have to get. But all in all, they will give us the same thing, right? So for KMNO4, take note of the condition. For the osmium, the first step is the osmium. The second step is when you use sodium sulfite, not sodium sulfate, sodium sulfite, right? Or you can use sodium hydrogen sulfite in water to also make the reaction occur. Right now, the reaction occurred to give us a glycol. So the glycol, what will happen here is that if we have not seen the change, is that when the double bond breaks like this, OH is formed here and another OH is here. When the double bond is broken, OH is here, OH is here. We have to be able to predict the products from what we have written. Very simple, right? Now, the effects are here. Osmium tetraoxide gives a higher yield. KMNO4 is powerful oxidizing agent and can easily further oxidize the glycol. Now, this mechanism, we can go through the mechanism, but we will not be worried with the mechanism. The last most important concept that we have to learn today is polymerization of alkenes. And so we are saying that alkenes in the presence of a more concentrated sulfuric acid can react with another alkene to form a dimer. 3 monomeric units produce a trimer and 4 produce a tetramer. A number of large monomers is called a polymer. These are terms that we can keep in our heads. Dimerization in sulfuric acid occurs in alkene to form tertiary carbocations. Very important concept. Because a carbocation intermediate is formed, it is called a cationic polymerization. Now, this is a mechanism which I will use a white screen to illustrate, and this is the last mechanism that we will talk about, and then we'll call it a day. So we are sharing a white screen. Oh. I should have taken note of the example I am about to solve. So let me go back and then look at the compound. So the compound I have to work with here is okay. Now I've gotten the compound. Okay, back to my white screen. So this is my compound. Okay, so this is it. Now, the first thing, the sulfuric acid. I've shown us why we can draw sulfuric acid like this, right? Good. Let me space in this a little bit so that it can be clearer. H, because we want to show the H in a reaction. Now, always what will happen here is that the pi bond will attack the hydrogen. And so what we have as a first step is we'll get this. Now the hydrogen coming here can be attached to this one or this one, but per the mechanical addition, it will be attached to this one because it has more hydrogens. Let's not forget. We have C here. Nothing has changed about the CH3 here. Nothing has changed about the CH3 here. Then the C. Then this one becomes CH3 because I've added this hydrogen to it. And then this one has a plus because it has lost the double bond. Now there's a side product, which is the OSO3H minus, because this bond will break onto this oxygen. This is the first step. Now, when we get this first step, the next reaction is that one of these, we are talking about dimerization. So we have two of these molecules. So another molecule of this compound. So let me draw the same molecule here again. CH3, C, CH3, C double bond CH2. Because pi bonds always have more electrons, right? It would attack this carbocation. So the arrow is coming from the pi bond to this carbon. Always, we should have to be careful of where the arrow is moving from to where it is moving to. You understand? Yes. Now, there will be coordination. The coordination will occur between this carbon and then the tertiary carbon here. These are very important things that we have to take note of. And so I am drawing this one. I'm drawing it, I'm drawing from the tertiary carbocation. If you draw this tertiary carbocation, you realize that it has three CH3 groups around it. So there's CH3 here, CH3, and this is not nice. There's CH3, there's CH3 here, there's CH3 here, there's CH3 here. Now, there's a new coordination here between this carbon and then this one. So we have this, then we have CH2, which shows this carbon. The C2 is this carbon. Now, we would have C. The C is now this carbon. Let me change the ink so that we can get to know the C. So the C is this carbon, right? Good. Then we would have the CH3 here, the CH3 here, right? Now, this carbon, because it has lost the pi bonds. The pi bond was shared between this carbon and then this carbon. Now, it has broken such that this carbon has formed a new bond with this, right? And so this is the carbon that has lost the electron. So we have a plus sign here. Now, when you get the plus sign here, the next thing is that the carbocation will ask itself whether they can be arranged to form more stable. The carbocation we have here is tertiary. It was in the notes that we read already that it will form to form a tertiary proceed. The dimerization proceeds to form tertiary carbocation. Good. Now, when we get here, the next step is that the carbons adjacent to the carbocation would have to lose hydrogens. Now, they will lose hydrogens such that there can be unsaturation. But then if you look at this very well, the environment of the carbocation, it has three carbons attached, 1, 2, 3. Now, this C3 is the same as this one. That means we can just take any of them, right? And then this one is a different environment, so we can also consider that. And so what will come and take the protons here? Let me do something. Now I am isolating the protons. It's the same thing, but I am isolating the protons. So I would have CH, instead of CH, I have CH2, H here. Now, instead of CH2 here, I just want to isolate one of the protons. I'll have another proton here. Now, what will come in to come and take the proton is this one, the OS3 hydrogen, right? H. So it would use the electron to either take this one. Now, if you are taking this one, we can have product A. If we are taking this one, we can have product B. Keep in mind that it will not take the two at the same time. These are two different mechanisms or reaction pathway. So if we are going with A, then we would get something like this. This one, the bond here will break onto this to form an unsaturation between this and this. So very simple, we would have a compound like this. CH2, double bond C, CH3, CH2. This is CH2 because I've not done anything to this one yet. Then I have CH3, CH3, CH3. So this is product A. Now, if you are talking about product B, it means that when this one removes the proton, the bond will be broken from here to here. So the double bond will be formed between this and this. And so we would have CH3 because this one has not been touched in the case of B. So we have CH3 here, CH3 here, then there's CH3 here, right? There's double bond CH, then there's CH3, CH3, CH3. So this is what we would have. Very simple. This is what we'll have. Very simple, right? So we have our two products here. Now we can still predict which of the product is a more stable product. Which of the product is a more stable product. Now, in order to predict this, we will use the z-test, which is the poor will get poorer. Now, if you look at the two options we had, this carbon had 3 hydrogens, this carbon had 2 hydrogens. Now, removing a hydrogen from the one that has a lower one is the poor getting poorer. It means the B here is the more stable product, is the major product. That's the dimerization, right? But the actual chemistry here is that this one here is the more substituted. The more substituted one is the most stable one. Very simple. Very simple. Right? So that is the mechanism. And then our record that we have to practice in order to master the mechanism. Now it has been illustrated here. Same thing. The alkene attacking the hydrogen, the bond breaking here. You form your anion, and then you form your carbocation. Then another molecule would attack the carbocation. The alkene will attack the carbocation. You form another tertiary carbocation. Then there are two ways of losing the hydrogen. Either use it from a CH3 or you lose it from here, right? The CH to the methylene group in the middle. And that will give us two different products, right? From which we can predict our major product, right? Yes, and our major product would most preferably go to any subsequent reaction that we have to go to. Now, from the dimerization, there can be more to get polymerization. So we are saying that polymerization of alkene, polyethylene, a high molecular weight polymer of ethylene is prepared on a large scale by free radical polymerization. Ethylene is heated at high pressure in the presence of oxygen or a peroxide, right? So this is the mechanism. This is just a reaction to show the polymerization of ethylene, right? Ethylene in the presence of what? peroxide, and then high temperature to form the polyethylene. So this is the last slide. And thank you very much for your audience. As I said, if you have any question, you can see any member of the HESA Academic Board. Thank you very much and all the best.